Hey everyone, and welcome back to another MECH 220 video. Today we'll be covering section 20.4, rotating frames in 3D, and we'll be doing example 20-41. Let's go ahead and read the problem. At the instant shown, the arm AB is rotating about the fixed pin A with an angular velocity 4 rad per second and an angular acceleration of 3 rad per second squared. At the same instant, rod BD is rotating relative to rod AB with an angular velocity of 5 rad per second, which is increasing at 7 rad per second squared. Also, the color C is moving along rod BD with a velocity of 3 meters per second and an acceleration of 2 meters per second squared, both measured relative to the rod. Determine the velocity and acceleration of the collar at this instant. So like last time, I have a few notes here written down that will be relevant to the problem. It's essentially when to use which type of equation. So we have shorter equations for velocity and acceleration. We have much longer equations for velocity and acceleration. The longer ones I have written down here. And essentially use the shorter one when you're dealing with 2 points on the same rigid body. So like for example, AB here, this would be considered a single rigid body. And if you had to deal with the rod AB, and we will later on in this problem, you will see that we could use those equations there. As opposed to the longer versions of velocity and acceleration here, we use these when we deal with 2 moving points on different rigid bodies, and or when we see that there's a translation relative to a rotating frame. So right off the bat, we can see that we will be needing the longer versions of velocity and acceleration because we're asked to find the velocity and acceleration of this collar that's moving away from the rod AB. So we know that it's a translation occurring relative to a rotating frame, and that rotating frame is AB, and then also the y-axis that's rotating that way. So to start off this problem, I have already written down the main equations that we will be using, which is the velocity at C, which is the velocity of the collar which we're looking for, and the acceleration at C, and all of that with respect to B. I have here written blue little aspects having to do with rotating frames, XYZ being the rotating frame that we're working in, which is essentially this frame right here. And then the velocity of the rotating frame and acceleration of the rotating frame, well, those will be found using concepts we used in the previous example that I did on general 3D motion. So let's start the problem. So R of C with respect to B is given to us here. C with respect to B is none other than 0.6. Oh, that's equal. And that's in the I hat direction. And that's in meters. We have V of C with respect to B and within the rotating frame, and that was given to us. That's 3 meters per second, and then also I think it also hints at it in the problem, both measured relative. Oh, that's the line. Both measured relative to the rod. So that's sort of a hint as well, and that is 3 I hat meters per second squared. And then, believe it or not, we do have, or rather, we can find the velocity of the rotating frame because that's essentially the sum of the angular velocities that we have in the problem, like last time. So that's none other than 4 I hat plus 5 j hat rads per second. So if we look at this expression, essentially what we don't have is VB. And in this case, we have to pay close attention to the fact that B is not a fixed point. B is moving with the rod AB, so it's actually moving that way. So because it's part of a rigid body, we can just solve for VB with our shorter velocity equation with respect to A. So that's what we're going to do. Now, the point A is a fixed point. It's a pin joint, so it's not really doing anything. So we can say it's 0. The angular velocity of b with respect to a, well, that's just the angular velocity, that's just omega 1. So it's 4I cross negative 1.5 k hat. And I say negative 1.5 because we're looking for velocity of b with respect to a, so it's a vector pointing downward like that in the negative k direction. So if you compute that cross product, you will get 6 j hat, and that is in meters per second. So we have all the variables that we need to find the velocity of the collar, so we're just going to plug all of those values in. And if you compute that cross product, you should get 3I hat plus 6j hat minus 3k hat. And all of that is in meters per second. Right, and that is the first part of our problem done. Next, we're going to move on to the acceleration at c. So we have our c with respect to b, which we know to be 0.6I hat. And then for the same reason that we know the velocity of c with respect to b, we know the acceleration of c with respect to b. And they gave it to us, that's 2 meters per second squared. Oh, and you put in vector form in the I hat direction, meters per second squared. We have velocity of c with respect to b, 3 I hat meters per second, and we have the angular velocity of the rotating frame. If you go back to our initial equation here for acceleration, where essentially we need to find is the acceleration of the rotating frame and the acceleration at b. And for the acceleration of b, we're basically going to use the same method that we used to find the velocity at b. We're just going to find the acceleration at b from the point A. This is just 0 because the point A is not moving, and then because the point A is not moving, this is essentially just VB. So we're just going to plug in all those values. Right. Now we only have one more thing to solve before we find the acceleration of the collar, and that's the angular acceleration of c with respect to b. Now I've talked about why this is written the way it is, but I'm just going to reiterate it. So they've already given an order to the velocities and acceleration in this problem. We know that omega 1 is first because they told us that it was omega 1, so it comes first. So we know that omega 1 is the standalone acceleration here, and then omega 2 is all of this. Where it's omega 2, the acceleration, omega 2 within the rotating frame, and then omega 1 cross omega 2, because with respect to omega 2, or rather with respect to the acceleration of omega 2, it is happening within this rotating frame. So this is why we add all of this. We're just going to plug in those values as they were given to us in the problem. So if you compute the cross product, you will get that the angular acceleration of c with respect to b is 3I hat plus 7j hat plus 20k hat rad per second squared. Now we finally have all the variables that we need to compute the acceleration at c. And again, this is very long, so I'm just going to plug in the values right away because I have my equation written at the top of the page. And that concludes this problem. Yeah. So I hope this was helpful, and thank you for listening.